Prior to the various resets by the controllers or colonizers of our world, music was a more natural thing. Unlike today's modern music, ancient music was untempered by man, meaning it wasn't mistuned by man-made mathematical methods. Music was simpler then, and instruments were tuned according to what was pleasing to the ear, rather than by mathematical formulas based on square roots, as is done today. The need for man-made musical temperament, or what I call the mistuning of music, arose from a problem inherent to stacking fifths, a problem called the Pythagorean comma, after the ancient Greek mathematician who discovered many mathematical properties of music around 550 BC. And although stacking fifths to produce a scale around the circle of fifths generates beautiful intervals based on whole number ratios, the problem is that it fails to resolve the octave as it cycles back around to C. Instead of a doubled C frequency, the octave C ends up slightly sharp, and this gap between the expected and the actual frequencies is known as a comma. So, for thousands of years, man has been tinkering with music, or tempering music, to try to resolve the Pythagorean comma, and the ancient Greeks were the first to have discovered and articulated this need for temperament. However, other forms of music evolved alongside tempered music without recognizing any such need. Music we might describe as indigenous is usually untempered and every bit as beautiful, in some ways maybe more so. The music of Native Americans, of India and Indonesia, music we might describe as Eastern European or Tartarian, is all considered to be natural and untempered music. And these instruments from China show the ancients using sets of 16 notes rather than our modern traditional 12. Those who have historically promoted musical temperament, especially the Greek philosopher Plato, have seen temperament as necessary to create a more cultured or civilized form of music. Though the temperaments used often achieve their goals for the octave by creating unpleasant distortions in the intervals between musical frequencies. The need for temperament as a Western ideal has been pitted against Eastern, indigenous, or Tartarian music. And so it's not surprising to see the word Tartar defined by Charles Mackay in 1888 as a great noise. It sounds exactly how the civilized Greeks described barbarous people lacking proper state governance and its resulting temperance. As a concept, musical temperament seems to hold a prominent place in the controller's reset paradigm. The Greeks were the first to temper their music, and they're said to have tempered it with thirds. In my book, The Next Octave, I quote extensively from Ernest Maclean's book, The Pythagorean Plato. And in it he states that Pythagorean tuning functioned as a kind of temperament for the Greeks. Unfortunately, Maclean didn't really elaborate on this, but his claim was clarified by Richard Heath. When Maclean proposed that Pythagorean tuning functioned as a kind of temperament for the Greeks, he is therefore saying that the Greeks filled octaves with fifths, but then tempered them with thirds. But what does that even mean? To better understand this ancient Greek idea of filling octaves and tempering with thirds, we need to look at Plato's mathematical description of the creation of the world soul in his book Timaeus. Here, Plato describes both the divisive and creative actions taken by the demiurge. And he began making the division thus. First he took one portion from the whole, then he took a portion double of this, then a third portion, half as much again, as the second portion, that is, 3 times as much as the first. The fourth portion he took was twice as much as the second, the fifth 3 times as much as the third, the sixth 8 times as much as the first, and the seventh 27 times as much as the first. Plato's creation of the world soul is depicted in Crantor's Lambda, a visual representation put together by one of Plato's students, Crantor of Soli. Crantor's Lambda illustrates some musical realities as well. While the left side of this lambda is producing octaves based on the power of 2, the right side is producing fifths based on the power of 3. And it's this process of stacking fifths that causes the musical problem of the Pythagorean comma. If we build a scale by stacking fifths, we find that we're following the right side of Crantor's lambda. The lambda and the circle of fifths correlate because in the harmonic series, C is harmonic 1, G is harmonic 3, D is harmonic 9, and A is harmonic 27. If we extend Crantor's lambda to one more place by tripling 27, we get 81. And if we stack one more fifth on top of A at the 27th harmonic, we generate an E at the 81st harmonic, or 81 Hertz. But this is not what happens in the harmonic series. Here, the scale isn't built by stacking fifths. It's built by the division of means, and for more information on that, you can check out my other videos or my book, The Next Octave. In the harmonic series, the chromatic scale is built 1 Hertz frequency at a time, but the order of the build is important. The note of E in the harmonic series is generated at harmonic 5, but is actually the third note to be generated in the series after C and G. E at harmonic 5 then scales up to an E octave of 80 Hertz, 1 Hertz less than the E81 that's generated by stacking fifths. And it's this value of 81 in the circle of fifths that begins an increase of every subsequent note's frequency in the scale, resulting in a C octave note that's too sharp, causing the Pythagorean comma. What we're seeing occur in the harmonic series, then, is a natural temperament that allows for the perfectly doubled octave of C that's missing in the Pythagorean circle of fifths. And the tool used by the harmonic series to temper the C scale is called a harmonic mean. To understand this better, we can go back to Plato's description of the creation of the world soul in Timaeus, where he talks about inserting 2 means into each interval. After that, he went on to fill up the intervals in the series of the powers of 2 and the intervals in the series of powers of 3 in the following manner. He cut off yet further portions from the original mixture and set them in between the portions above rehearsed, so as to place 2 means in each interval. One a mean which exceeded its extremes, and was by them exceeded by the same proportional part or fraction of each of the extremes respectively. So let's go over this in detail, because it's not as difficult to comprehend as it might sound. Plato is saying that there will be 2 means placed inside each interval. One is a mean that exceeds its extremes and is by them exceeded by the same proportion. Now a mean is a midpoint between 2 extremes that exceeds its lower extreme, so it's above it, and is exceeded by its upper extreme, so it's below it. It will land somewhere within this interval, depending on what kind of mean it is. Plato gives the detail that this mean both exceeds and is exceeded by the same proportion. This is the description of a harmonic mean, which can be calculated by the formula of 2ab over a plus b. If we place a harmonic mean in the interval here, between 3 and 9, the resulting value would be 4.5. It exceeds the first extreme by 1.5, which is half of that extreme, and 9 exceeds 4.5 by half of itself as well. The second mean Plato describes being placed into the interval is one that exceeds one extreme by the same number as it's exceeded by its other extreme. This is a description of an arithmetic mean, which can be calculated by the formula of a plus b divided by 2. If we place an arithmetic mean in the interval here between 3 and 9, the resulting value would be 6. It exceeds one extreme by 3 and is exceeded by the other extreme by the same number, 3. These two means, the harmonic and arithmetic, are the ones Plato says are placed in all the intervals, including those of the power of 2 and the power of 3. We can see that the arithmetic mean is always at the midpoint, or mies, between the tonic and the octave, but likewise, the harmonic mean is always at the midpoint, or mies, between the tonic and the arithmetic mean. We might even say that the harmonic mean is a kind of meta-mies, the mies of the mies, and it's this meta-mies, the harmonic mean, that produces a temperament of the C scale. We can see this very thing taking place in the harmonic series as it generates the structural beams of the chromatic scale, which I discuss in my book. Aside from the octave repeats of the note of C, which occur in every even-numbered harmonic between 1 and 16, the odd numbers generate new notes that serve as structural beams for the chromatic scale to come. The first beam is harmonic 3, the perfect fifth sitting at the midpoint or mies of the C octave. The next beam, generating again as an odd number, is harmonic 5, the E or major third sitting at the midpoint of the tonic of C and the mies of G. So instead of allowing the power of 3 to iterate its next fifth of E at 81 Hz, the harmonic series instead reverts back to the power of 2 and generates that E here at the harmonic mean, showing up on the lambda as 1.25 Hz. The harmonic mean then scales up to 2.5 Hz, 5 Hz, 10 Hz, and on up to harmonic mean 80. And this reduction from 81 Hz to 80 prevents the entire scale from shifting sharp and creating the sharp octave known as the Pythagorean comma. And when we realize that within the C octave, E is the major third and G is the perfect fifth, we're reminded of Richard Heath's statement that the Greeks filled octaves with fifths, or arithmetic means, but then tempered them with thirds, or harmonic means. Why does the metamies work in this way? It's because the harmonic series itself is based on the power of 2. That doesn't mean it produces no 3-based frequencies, it certainly does, but the intervals inherent to the harmonic series are all 1 Hz, and as we learned from Rodin's Mobius circuit, the number 1 is part of the series 124875, which is based on the power of 2. And while the mies of the scale is harmonic 3, based on the power of 3, the tempering third is harmonic 5, a member of the 124875 series. Once again, it's this tension between the powers of 3 and 2 that produces both beautiful and functional musical intervals. So the Greeks were really just using harmonic tuning with the metamies, as this is how the harmonic series tempers the C scale to produce a resolving doubled octave. But although Plato was overtly defining the natural form of harmonic temperament in Timaeus, he was covertly encoding other forms of musical temperament into his work. And this is the subject of Maclean's book, The Pythagorean Plato. Early on in Maclean's book, He states that from a musician's perspective, Plato's Republic embodies a treatise on equal temperament. And this is the form of temperament or musical distortion that we have today. Modern music utilizes equal temperament, a system that employed genius math to distort the intervals we've all grown up hearing. In fact, we're so programmed to these distorted intervals of equal temperament that we're susceptible to thinking harmonic intervals sound off. Man-made temperaments are much more dissonant and distorted than a natural temperament like a harmonic mean. And that's why it's so important to make sure we listen to a fair amount of naturally tempered music regularly. Music we might describe as Tartarian or indigenous. Really, any music unlikely to be broadcast over the mainstream airwaves. Retraining our ears will allow us to become accustomed and to recognize intervals that are naturally tempered and justly intonated. Even a simple singing bowl can help us retrain the ear. This is mine. I'm grateful for any feedback. Please leave your thoughts in the comments, and thank you for watching.